Hey everyone, let's get started. I'm Pete Zielinski, Editor-in-Chief of Additive Manufacturing Magazine. Welcome to today's webinar titled Solving the High Cost of Low-Volume Plastic Parts, brought to you by Plural Additive Manufacturing. An adopter of Plural's 3D printing technology, PMT, Plastic Metals Technologies, provides conductive coatings to components used in the aerospace, defense, and medical industries. Adam Anaforian from PMT, along with Ed Israel from Plural, are going to talk about how PMT has reduced its costs while improving its capabilities by adopting additive manufacturing to produce its needed tooling. While these guys are speaking today, you can submit questions. Do that using the questions pane at the right of your screen. We'll see the questions that come in, and at the end of the talk, we'll answer as many as we can. With that, Adam and Ed, if you're ready, please begin.
Thank you very much, Pete, and I also want to thank Gardner Media for hosting this event. I want to briefly just show you the agenda here. We're going to talk about how we met, the problem, the goals that Adam was looking to achieve, the environment, and the three bears of AM. You'll have to share that with me, Adam. And then obviously some of their new capabilities. We believe that we're at the cusp of the additive manufacturing movement. We're at the very early stages of it, yet we're seeing some really cool successes in this market today, and PMT happens to be one of them. We've got a poll question coming out to you now, so please take just a moment to review it. And Adam, while they're doing that, let me ask you a question. So how is business at PMT, and why, do you think?
Sure, yeah, business has been really great. 2017 was a really great year for us. I think it was a record year. This year's, we haven't really slowed down. Usually there's a dip in January. And I think the reason for that is a couple parts. There's a lot of confidence, I think, in the economy, which is helping a lot of our medical customers just making more sales changes in the medical industry. Also, a lot of projects that we've had for a long time are ramping up, so that's been really good. So some of our big customers are ramping up, so that's been really good too. And then our aerospace defense, that's growing a lot as well. So just across the board, in addition to new projects. So we got a lot of new projects that are spinning up.
Nice, nice. So hopefully there's been enough time. We're going to share those poll results now. And so an interesting story here. We had a customer that was machining an RF shield. That is this item right here, actually this item right here. And they were paying about $600 for one to have it machined out of aluminum, and it took somewhere between 4 to 6 weeks to get. They approached us and they said if we had any ideas of how we might be able to improve that time. So what we did is we got the file, we ended up printing it, as you can see here, in plastic, and that took about 11 hours overnight, probably less than $15 worth of material. And then PMT basically metallized that part, and then we compared it in terms of how well it worked as a shield over a circuit board versus the aluminum, and it worked quite well, actually almost identical to the aluminum. But while we were touring PMT, we saw all of these 3D printed parts lying around, and I asked Adam a bit about the parts and what he was using them for, and I found out basically that they were using a service bureau, and they had spent somewhere in the neighborhood of, I think, $30,000 going outside for parts in about a 7-month period. And so that got me thinking, and kind of the rest is history, and obviously more of that will come out as we talk a bit more. So Adam, why don't you share with us the problem, and the biggest problem we see in the industry, which is obviously the title of our event, is low volume plastic parts just cost too much.
Yeah, and that is primarily what our biggest issue was. Is it's expensive to have parts machined. It was a little less expensive to have them printed through a service bureau, but primarily just expensive because we do high volume of parts that we process for our customers. But when we're building tooling, the components are a lot smaller, or less volume needed, I should say. And so low volume to a machine shop, sending them 10 parts to machine for us or 10 parts to print at a service bureau is just cost prohibitive. Sometimes a lot of times our customers squeezing us for price. So that was a big problem for us. We needed to be able to save money. That's the primary driver. And, we had to iterate, or we didn't get it right the first time on our design, or we find out that the customer's part's not quite what it says on the drawing, and we have to iterate, then we're out more money. So just overall cost.
A good problem.
It's a problem, yeah. So our primary goals with bringing in additive was to wanted to reduce cost. Obviously, that was the biggest driver. And we also realized that a lot of times we didn't have control of the process. So we could send a part out. We're designing for manufacturability. We send it to the machinist, and sometimes it didn't come out like we wanted, or the surface continuity wasn't good. The quality of if we're trying to save money, send it to Joe Machinist down the street, we wouldn't get the good quality. We get the price, but we wouldn't get the quality. So if we wanted to send it to somebody that's going to do a good job, has the right machining, it's going to cost too much money. So our goal was to just reduce cost primarily. We wanted more control over the process, and then we also wanted to be able to decrease the lead time. So this is what you're seeing here, some pictures of our fixtures. So our environment is we do vacuum metallization or physical vapor deposition, and we're processing hundreds of parts at a time in one day. There's some parts where we'll do a couple thousand. High product mix, high volume, high mix. So we put all these parts into a vacuum chamber. We pull vacuum to very low vacuum, low atmosphere, and then we evaporate metal, and that metal bonds with the customer's parts that are floating around in our vacuum chamber. Basically, they're fixed in our machines. Our process is line of sight, so we need really good tolerances on our masking. Any part of the substrate that we're coating that is not covered is going to be coated with the metal after we evaporate it. So it's really important that we mask very detailed features. So that's kind of our environment. So it's really important that our machine components are, the tolerances are very tight, very important.
Got it.
So we could have just a few thousandths of play in between plastic and metal.
Got it. Actually, I'm going to do a no-no. I'm going to go back in the slides and show all of you very quickly. This is an example of one of their customer parts. This is an example of one of the fixtures that had a really tight tolerance to it, with actually a little lip that falls into this groove. And I think, Adam, what you had mentioned to me was that this part is repeated, I don't know how many times, 50, 60, 100 times in terms of preparing fixtures. Mm-hmm. So you need that constant dimensional accuracy and repeatability every time you print.
Yeah, absolutely. Yeah, we'll load now on our printer, we'll load a build plate full of these parts, and they all need to do the same thing. And you can tell by that little feature there, it needs to be spot on. We actually had to do a couple test prints and adjust, and once we nailed it, all the parts are fitting well. This is for a project we're currently building right now.
Beautiful. I'll head back to where we were then.
So the three bears of additive. I'm not going to take 100% credit for the illustration,
but we can call you Goldilocks here.
Okay. We had some very creative people come up with this illustration, but we're going to go. This is to kind of illustrate our journey from to additive, to bringing in 3D printing in house. So our journey was, we started off with machining, having parts machined. Could be cost prohibitive, had issues with quality control if we wanted to save money. And then we went to service bureau, and then on to bringing it in-house. So what you see here on this slide says machining too hot. This porridge is too hot to go with the Goldilocks and the three bears. illustration. So we have a machine plug mold here, and so for some of our customers' parts, you've seen some of these, some of the green components on the previous slide. Those are nest blocks. So our parts go into the nest blocks, and they're held in place in the fixtures by those nest blocks, which we now print. But for some parts that are still going to be exposed to the evaporated material, we need to mask those, and so we make custom molds, like you see here in this photo. To pour silicone in, and we use that poured silicone to mask the parts, so we don't get metal where a customer doesn't require metal. So we put too hot, the machine plug mold. We do have lead time issues with these in the past. We had to wait a couple weeks sometimes, and the customer wants, they want them next week, and we got to wait 2 weeks just before we can get the plug mold to get the masking, and problematic. And because we're only doing 1 or 2 of these molds at a time, it's very cost prohibitive. So that was a big factor for us. Is we could get the results we wanted if we wanted to pay, but we had to wait, and it's a lot of money. So, Service Bureau, we're getting better, but it's too cold. What you see here on the slide is a 3D printed nest block fixture in green. We have one on each side, and you can't really see all of the features that are what's going on the other end, but there's some very tight lips that are basically serve as cutoffs, so that there's a very fine delineation between the metal and the plastic. But here we were able to decrease our lead time. We were able to decrease the spend a little bit, but it was still expensive. And at the short runs we did, cost was still a big factor for us. So we also didn't have the control we wanted, and I think that was another driver why we wanted to get into 3D printing. But I do think when we started using the service bureaus is when we started really looking at the potential to bring in 3D printing, because we saw other people were doing this. People are starting up companies that are just 3D printing parts for people, and we thought, this might be something we could do. However, we always thought the price point was a little bit cost prohibitive. The cost to enter was a little bit too great.
So Adam, these are the green nest blocks that you're talking about right here that needed the precision, and this is an example of some of the masking right here.
Exactly.
That needed to be done, some of the manual masking. Okay, thank you.
So in-house 3D printing, this forge is just right. So again, I can't take credit for that. That's all.
Oh, don't put that on me.
So lower cost was obviously that was our primary goal, is to save money. We're not a large operation. We're growing, but a lot of the cost to enter is very expensive for 3D printing. But we needed to figure out a way to save money on these components. So we found that it to be, and these numbers are conservative, but 50% lower than the service bureaus, and 70% lower than machine shops. And I honestly could say that's probably pretty conservative for a lot of the machine shops we were using. We were able to decrease the lead time initially. Now we're printing so much, and we'll talk about this a little bit more. We print more now. We actually fabricate more parts for tooling, because we've been able to improve our process, that now we're using it so much that we are now getting a lead time out there. So we're probably going to be looking to bring in another machine here soon. So we've been able to decrease the lead time initially to days of lead time, and we had greater process control, which was huge for us. The ability to iterate quickly was also very important, and we were able to do that now, because if something's off on the design, or the tolerance wasn't right on the part per the drawing from our customer, we were able to be a little more nimble, and we could print a new part and test it out the next day. So that's been awesome. And then new design solutions is kind of what I already talked about. But yeah.
I think you mentioned to me that when you were first looking at a printer, you were trying to decide, could you really keep it 100% busy? But that first printer was paid off in about 7 months, and the second printer now, you expect to be paid off in about 5 months?
I think it's probably paid off now. I think we bought it in October, November, but I'll need to, from Jason's projections, that's what we were on track to do. So
very cool.
All right, so here's a couple examples that we're going to show you of what we've been able to do and how we've been able to consolidate some of our fixtures. So what you're looking at here on the top picture is This is a machined metal part. There's two parts, and what we ended up needing to do is these parts nest a large part in a big metal fixture, and the part nestles into these little parts that you see here. So the two parts on top were combined into one to create a lip, and that lip provides masking for metal and also allows the part to rest and nest into our fixture. In order to get that, our old solution would be to combine two metal parts. We have a machine, we drill out holes, and we make two parts. So you see that part below in the picture below, combined, still metal, and you see the little lip. I don't know if you can see that in the presentation. And then below that is the 3D printed part, where we were able to completely replace that with one printed component. It's a lot more elegant, and it contours the part. And an added benefit that we didn't anticipate was over time with the metal parts, what we would see was the parts would start to wear and the metal would actually scratch the plastic parts that we were coating. And so the plastic, the ASA material that we use, has actually been an improvement for us because it doesn't scratch plastic on plastic. So the next slide here, you're going to see where we actually took a four-piece assembly for one part, and we were able to combine it into one. You're looking at machined Delrin and machined metal, and the metal is very thin. The part would nest into the machined Delrin, and then the metal would kind of make a lip around the part so that we had a delineation between the plastic and the metal. It basically masked the part for us. Problem with using metal is over time we're loading parts in constantly. The metal would bend. It would allow overspray from our material to fall onto the part, create more cleaning for our inspection, so it added labor. But also when the metal bends, it can scratch the parts, and so we've had that happen a lot, which could lead to quality concerns, possible rejects. We hate seeing parts go to MRB. So we were able to consolidate that down into the black piece that you see on the slide. A lot more elegant. It's one piece. The assembly is straightforward because all of the screws are easy to locate. Our people that assemble our shields can just basically pop it on without having to make any adjustments, and it's ready to go. So that's been awesome.
So Adam, this particular part, you needed it to, it was also another high precision part. So the service bureau that you used originally to print these parts was one that you knew had good industrial printers at them. And so
yeah, we had it quoted. Yeah,
and the quote on that was somewhere in the neighborhood of $192. Now there are service bureaus out there that could do this anywhere from well under 100 to probably over 200, but you were quoted 192. We'll show you a little bit later the costing model for this particular part to show you what their fully burdened cost was on this part.
So why is Vic smiling? So this is Vic. He is a process engineer at PMT. He's been with us for 10 years. He has seen it all. He builds all of our fixtures, he maintains them, and he works with engineering. So engineering does the design work, he does the building. And he's smiling, and if you don't know Vic, he's actually beaming. It doesn't really look like he's smiling, but he's stoked. It's really changed his ability to quickly, because we're getting busier, to quickly build shields. The maintenance, there's a lot less maintenance now because a lot of these components that would wear or bend. He doesn't have to do that anymore as often. And if we do need to make an adjustment, or if one of these nest blocks ends up wearing over time, we just print a replacement. He has a few backups for a lot of these, so it's just a matter of disassembling and putting the new nest block on. It's just more efficient. It saved us a lot of time, and it's allowing us to be able to keep up with a lot of the new work that's coming.
Cool. So while this is not a poll question, if any of you in the audience know who this person is, please enter it into the question box, not the chat window. And whoever does that first, because it's time-stamped, you'll get a special gift from us. So this picture that you're looking at is from the 1968 Olympics. It represents one of the greatest aha moments, literally, in the history track and field for the Olympics. If someone knew the name, I'm going to say it now because many of you could have gone off to the web and tried to find that name, but his name is Dick Fosbury. And a few years before the Olympics, he was doing this particular style, which is now called the Fosbury flop. He was being admonished for it. There were people who looked at him and thought, you know, he's not going anywhere with this. He actually started it in high school, believe it or not. And he won the gold medal in 1968 with a world record. And and within 2 to 3 years after that Olympics, 13 of the top 16 high jumpers in the world were using this style. And the reason that we're showing this here is because it's about thinking differently. This is the supreme example of somebody who thought differently from a physics standpoint, from a motion, standpoint, how he might improve what he's going to do and actually improve his sport. And so there's a term that most of you probably know in the industry, design for manufacturability. And what that says is that the design engineer needs to collaborate with the manufacturing engineer so that the designer designs something that the machine can print. And so there are constraints, obviously, with all machinery out there, especially in the traditional machinery, constraints related to printing hollows, printing variable wall thicknesses, a range of other things that you're not able to do in traditional machining or injection molding processes. So that's DFM. The term in the market for the world we live in today is design for additive manufacturability, which have very few, if any, constraints in terms of how you might design a product. So basically, the idea of rethinking products from a weight standpoint, from a shape standpoint, from a cost standpoint, is totally available now to the design engineer. And so, Adam, with that concept of thinking differently, can you share a bit about how your company has thought differently about design and other things as it related to bringing these systems in-house?
Sure. Yeah, I think initially our first goal was to just save on cost. Once we got the machine in and started printing, we just started realizing we can print so much more than the applications we saw initially, which were just like the nest blocks that you saw. We were like, well, why don't we try printing pluggable? And I think engineering has realized now in the past where they've had to sacrifice creativity for cost because of the
or even ability.
Yeah, ability.
Yeah,
and when I say creativity, I mean if we could do it this way, it would be great. But if we want those results, it's going to cost so much money. Now they know, well, let's try it and let's 3D print, and now we can iterate so quickly. So it's really off some of the shackles, I feel like, the things that were holding engineering back when we're designing tooling, because now we think, hey, well, what can we do with a 3D printer? How can we do that now? We've been able to design out in advance quality issues. So there are times in projects in the past where we're like, we're just not going to be able to get that we're just going to have to allow a little bit of metal overspray here, and we're just going to have to factor into cost that we're going to have to clean that in an inspection before we send out. Now we can actually design that out in advance. We've picked up new capabilities to do that. And a lot of that you've seen by how we consolidate parts assemblies for our fixtures. That's really changed things. We're able to deliver quicker to the customer. We can iterate quickly and prove out problems. So we've been able to decrease our NRE period. It used to be out there quite a ways. And now we're loaded down right now. So it's still, we're still a few weeks out for new projects, but it's gotten a lot better. We're not limited by the tools. So designing for manufacturing, like you said, one of our main design engineers doesn't have to think, oh, okay, well, am I going to have to design for this machine, and what's the cost going to be? It's going to be too much, because our customer has kind of this goal that they're trying to hit. So that's been awesome. So it's really changed kind of the whole approach. It's an integral part of our new product introduction phase now.
And you mentioned beaming Vic. I mean, you kind of mentioned me once before when I was taking the tour that he's kind of reborn in his own position. He's been there for 10 years, and it's like he's been there a year in this position in terms of his view on things.
Yeah, he's actually I definitely have noticed that he's a great guy, and he's always been a great part of the team, and he enjoys being there. But it seems like he's happier, honestly, with because now we've been able to really make things a lot easier for him. He's happy before, but you know, everybody likes it when you give them tools that help them do their job better or with less friction.
That's pretty cool. So we've talked a lot about cost. I hope you folks can see this spreadsheet well enough. But as we work with our customers and prospects around the country, one of the things we realized, and obviously I guess we've known this for a long time, is that probably the two most important things to manufacturers in making the decision to bring this kind of technology in-house is what's it going to cost me, or what's it going to save me, and what is the quality going to look like? Well, we've certainly addressed some of the quality things today, and Adam has certainly shared some of the costs. We actually built a tool a few years ago, and this wasn't a tool that we had actually planned on providing to our customers, but this is what we used actually with Adam to help them understand just exactly what their costs would be for printing any of their parts before they even had to acquire any technology. And so what you're looking at here is a cost per part, a fully burdened cost per part spreadsheet. The only thing that's not in here, and there's a lot more to this spreadsheet, but I'm just showing you one particular screen right now. If you'll notice, anything that's in yellow represent variables. So we've got just one part there, LVP nest part in there, and you could put other parts in there as well. Quantity of part was 1. We know what the amount of material is coming out of the slicer. We know what material we're going to use. You can select from a wide range of materials. We know what support material you're going to use. We know how much support material is being used out of the slicer. We know how long the print time is going to be from the slicer as well. So all of this information kicks out a material cost, a machine cost, and what we're seeing here is this particular nest part that you saw earlier that showed the 4 parts going into 1. Adam paid, his quote was $192, basically coming from the service bureau. As I mentioned, it could be in any of those numbers, but knowing that he would get the one that was close enough to what he wanted. The fully loaded cost per part for this particular part is $17.35, and that includes adding a materials management system, which is you can add other accessories. You can take those out and see how that changes the part costs. You can change, in this particular case, they're running 24/6. You can plug in 16 hours, 4 hours a day, and you'll see how the part costs change. So these are real numbers that you now have a really good sense on what parts, if you determine there are parts that are viable, what they cost, and all of these things. So your risk is really, really low. And so Adam uses this spreadsheet today as they start looking at costing. He'll plug in numbers. So it's a nice tool that you use that you find a value, right?
Yeah. We don't use it as much now because we've kind of
you already know.
Out. I mean, so now we buy materials and we keep it running. So
cool.
So our lessons learned: additive manufacturing is real. It can be extremely affordable. One thing, there's a bullet point on that's not on here that I wanted to say is it's accessible not just financially, but a lot of times for me, I'm not an engineer and I do a lot of the maintenance on the printer. It's very easy to set up. It's very easy to use and learn, and so it's approachable for people that aren't necessarily an engineer by trade. So that's one thing I just wanted to put in there. But the affordability was a big thing for us. That's the reason why we didn't, we had looked in the past into bringing in 3D printing, and the cost to enter was just too high for us. We're a small company, we're growing, but we don't have that huge budget to, spend whatever, $200,000 on bringing a printer in, unless we could really see what the value was. And so the fact we were able to quantify it with the spreadsheet do some sample parts. That was helpful for us. So definitely, my recommendation was what we did is look carefully at it. Make sure you're really doing your due diligence and making sure the numbers make sense to you, and make your vendor prove it.
Gee, thanks. So appreciate it, Adam. Hopefully you folks out there found the information of value. We're at a Q&A period right now. So please, any questions that you have or any that have come through, we'll answer them to the best of our ability.
It's Pete. I'm back, and we do indeed have some questions coming in. So let's just get right to that. First question. Adam, did you already have CAD design capabilities in-house prior to bringing in Additive?
Yes, yeah, we did. We designed our machine components. We have an engineer that designs all of them, and he would send them out to like service bureaus and have them quoted for the printed parts, and then for machine parts, you would, if it's a guy that we're working with locally, he'd get a drawing together and give it to the guy. So we did that in-house. Yes. Long answer.
Well, and actually, if I may just jump in real quick, there are a lot of design firms out there that are adding 3D printers to their, into their repertoire. So being able to look at different design firms that are out there and work with them as well are options.
Another question. How many builds are necessary to achieve a part that meets the tolerances you're describing? And the questioner is asking, are those trial builds incorporated into the kind of cost estimation that you were doing?
Oh, that's a great question. That's a great question. Let's see here.
Well, our cost, the numbers we gave you didn't factor they didn't factor you're talking about iterating, right? To make sure we're hitting the. Right?
Well, I think so. The without trying to make a sales pitch here, the tunability of the printer to dimensional accuracy is really high. You have an option with the printer to work with a slicer that is kind of a point and shoot slicer, or a slicer that you can drill deeply down on. And so, your engineer was able to actually go in and tune for certain types of tolerances to nail them. But I'm sorry, but I think in general, I'm sure there's been iterations where some of the costs haven't been included. So it's a great question, actually. I need to think more about how I might answer that at another time. But I think that's the answer that we would throw out at this point, unless you have anything else that you would share.
No, and I think for us, a lot of the times, if we have to do a redesign on something, it's usually because either there's a rev change in the middle of the new product phase, introduction phase, or it's very rare that the tuning is because our engineer didn't get it right the first time. They're pretty good. He gets it right good. We haven't had to adjust a lot for the printer. The printer usually does what he tells it to do, so that's been pretty nice. Working with the material we work with, we're not working with really crazy materials like, we're working with an ASA, which is it's polycarbonate, isn't it?
No, ASA is there's a PC ABS, which is a part polycarbonate, but ASA we like to think of as a little bit better ABS.
Okay.
So, but it's fundamentally ABS properties. And as I thought about this a little more, I should mention that all of the materials that Adam gets come with material profiles. And once those material profiles are loaded into the slicer, basically the system knows immediately how to tune for flow, how to tune for de-string, how to tune for temperature, all of those things. So generally speaking, the parts are going to come out round one at the tolerance that you can achieve. And we can achieve tolerances. We're comfortable saying, plus or minus 6 to 12 thou, but if we get down to tuning, we can get into some machining tolerances on some parts. I want to really say some parts, not all parts.
Ed, we're getting some questions that are just straightforwardly about the machine. One guy's asking what machine are they using for their builds. Another of our viewers is asking what's the technology of the printer? Is it FDM? Is it SLS? Why don't you talk a little bit about the machine?
Got it. So our company, first of all, is an additive manufacturing integrator, and very quickly we saw this huge gap in the marketplace between the hobby and prosumer printers that are just not going to cut it when you're looking at repeatable, highly accurate parts, and then what I call the world-leading products out there that are from the volumes that are out there that are pretty expensive with OEM captive materials. So we found a printer out of Italy. It's the 3NTR printer line, and we represent it for all of North America. It's FDM technology, and it is open materials, which is part of what gets those costs down. So we're able to use basically off-the-shelf materials. We tune those materials we set up the material profiles, and material profiles are really one of the true holy grails of printing properly. So Pete, I don't know, I may have missed another part of what there's two models on the printers. They're both identical. One has a build volume of 24 by 13 by almost 20. The other has a build volume of roughly 12 by 8 by 8. Very easy to maintain printers, 24 by 7 industrial printers. And we're without again trying to be too salesy, we're having good success with these around the country. But it's really about delivering exactly what the customer wants to see.
It's three nozzle printers too.
Thank you. They're 3 nozzle printers, so they're true multi-material printers. One for soluble support. The other, we're printing with rubber products, different soft polymers and hard products together. I'll stop though.
So about the use of the printer, Adam, one person here is asking, has your team put any threads, ID or OD, into any of these parts?
Oh, threads. We haven't really experimented. Honestly, we haven't really experimented a lot with threads. What we have done is we'll do like a guide hole, and then we'll use a tapping screw, like a plastic self-tapping screw. We haven't, let's see, what have we done? Yeah, even that project, I'm thinking about a project I did where I just ended up doing a metal insert because I wanted to. So we haven't really experimented with it, honestly, yet.
If I can jump in real quickly, which I have a tendency to do. We print a lot of threads, and whoever asked that question, feel free to send us the part file, and we'll print that for you and shoot it back to you at no charge, unless it's some humongous, gigantic part. But you could just take a cross section of the threads or just the thread portion of it. We're happy to do that for you. And I wish I knew the sizings off the top of my head right now, but we can print some relatively small thread count. The FDM technology, some of its limitations are getting down to really fine parts, but depending on the nozzle size and the bead, we can get to some pretty nice looking threads. And so if it's something you're interested in seeing if it can print, no commitment on your part, we'll shoot you that just for being a part of this webinar today.
So 256 threads?
I'll wait and see what they've got, but happy to do that. But we do a lot of printing with threads. But like Adam said, we also do a lot where you print the cavity or the hole. You can do a pause if you want, and you can do a metal insert right in the middle of the print, or afterward you can do a heat sink type of insert. So any of those things are options for you.
So questions keep coming, so we'll keep answering them. Adam mentioned that the printer cost, that he got the ROI in about 7 months, and he's asking, was that for the big machine or the little machine?
That was for the big machine. We have 2 of the A2s, which is the large machine.
Different question. For the parts you're producing, what kind of post-processing is involved?
Really, it's so we're working with primarily 2 materials. We really want to start experimenting with some other materials, but we don't have the time on the printers right now because we're keeping them so busy. But we're using ASA. ASA for the build material, and then HIPS, a HIPS breakaway material. And the way it's dialed in with the KISS slicer, it pulls away really nice. So if you have your nozzle calibrated, so if you run your calibrations, your X, Y, and your Z, everything's where it should be, it really breaks away really nicely. You just rip it off, and very rarely will I have to take like some other tool like an X-Acto knife or something to try to shave it. If your machine's calibrated, our experiences with those two materials, it's just breakaway material, and we have a really nice surface there. I will say we try to print an orientation wherever the breakaway material is going to be, the support material, that's not going to be a critical feature that's providing some sort of an important mask where surface finish is important. We do that just so that we can eliminate any sort of need to do any sort of sanding or smoothing of the surface. But the surface is pretty smooth anyways. But that's usually not a functional part of our fixture.
You can go to our website or go to our Plural YouTube channel. We just fired that off about a month ago, and we actually have a video that a customer submitted to us totally unsolicited because he had come from an industrial printing environment where everything they did was soluble support, and this was the first part he'd ever printed where he did with breakaway support, and there's a nice little 30-40 second video showing him breaking away the material. So and again, in the industrial 3D printing world, you want options for breakaway support, you want options for soluble support, and they're all there.
Couple more questions. Can you do variable Z height in terms of print a part at 10 thou layers for speed and then at 5 thou layers for detail?
Absolutely. The latest version of our slicer has just added a function called Adaptive Z, and I'm trying to remember if we have that on our website. We actually have a really neat part that we show smooth, smoother, smoothest. But what Adaptive Z is the system will look ahead and decide what the size needs to be. So if you've got, let's say, a part, wish I had the part right here. If you had a part with a straight edge that maybe has a curve heading up like to a dome, and you could set that to print between 0.15 millimeters and 0.3 millimeters. It will print the straight wall at 0.3 millimeters, and as it makes the curve, it will start changing the layers to get down to 0.15 to make a very, very smooth surface where that's important. So that's one thing that we have. The other thing that we have is the ability to, if you needed to hit, for example, a particular Z tolerance, and we actually have a video of a customer that needed to hit a Z tolerance of 0.901 inches. We can actually adjust that Z based on a simple formula, which we can show anybody, that they needed a 0.1976 Z to be able to hit that 0.901 Z height. And they had 6 points that needed to be hit. We hit 2 of them dead on, 2 of them 2 thou off, and 2 of them 3 thou off. So not only can we hit a fixed Z if you need it for a particular height, but we can also have that adaptive Z as well.
So last question is that spreadsheet that you used for costing, is that available? Is that a tool people can use?
Well, I like to say that with great power comes great responsibility. It's a relatively complex spreadsheet. So the answer is the following. If someone would allow me to show them how to use it, we would be happy to provide it to you. So, and also if anybody wanted to send a part, again, we can plug those part costs in and then do a web conference and show you the whole thing, or we can walk you through how to do it yourself with the spreadsheet. It's not something that we, as we look to automate it even more, maybe we'll see putting it on our website. But for now, I'd be happy to provide it to you as long as you gave us the opportunity to show it to you. Because there's parts of it that enable you to look at if I'm doing 60 a month, 80 a month, 100 a month, what is that cost going to be? Does it add a second printer? Where does it cross the line between injection molding and, where it may make more sense to do an injection molded part as opposed to a 3D printed part? So it has all those features in it. So happy to show that to you if you so desire.
All right, I think that does it. That concludes today's webinar. I want to thank our speakers, Adam Anaforian and Ed Israel, and I want to thank Plural Additive Manufacturing for making this webinar possible. Learn more at pluralam.com. An email with a link to a recording of this webinar should be coming to you soon. Thank you for your time today. I'm Pete Zielinski with Additive Manufacturing Magazine.